The universe is vast and mysterious, stretching beyond the limits of our imagination. We look up at the night sky and wonder, what lies beyond those twinkling stars? Where did it all come from? How did it all begin? The Big Bang Theory offers the best explanation we have for the origin of the universe. It tells a story of an incredible journey, from a tiny, almost inconceivable point to the vast cosmos we see today. In the beginning there was no space, no time, no matter as we know it. All the universe's matter and energy were compressed into an incredibly hot, dense state, a singularity. Then, about 13.8 billion years ago, something extraordinary happened. This singularity began to expand. This tiny point began to expand rapidly, in a process we now call the Big Bang. This wasn't an explosion in the usual sense, with debris flying outward. It was the expansion of space itself, stretching and growing. Imagine a tiny balloon suddenly inflating to an enormous size, carrying everything within it. That's closer to the picture of the Big Bang, an expansion of space and time. The Big Bang is the foundation of our understanding of the universe, the starting point of everything we know. But it's not just a beginning, it's a continuous process, a story still unfolding. Full of mystery and wonder, the universe continues to expand, revealing new secrets with every passing moment. How do we know the Big Bang happened? This question has intrigued scientists and astronomers for decades. Scientists have gathered a lot of evidence to support this theory. Through meticulous observations and advanced technology, they have pieced together a compelling narrative of our universe's origins. Let's explore some of the most compelling pieces. These pieces of evidence not only support the Big Bang theory but also help us understand the universe's evolution. First, we have the cosmic microwave background radiation. This is essentially the afterglow of the Big Bang, a faint light that fills the universe. It's like a faint afterglow of the Big Bang, a whisper of light coming from every direction in the universe. This radiation is a snapshot of the infant universe just 380,000 years after the Big Bang. Discovered in 1964 by Arno Penzias and Robert Wilson, this radiation confirms a key prediction of the Big Bang theory. Their discovery earned them the Nobel Prize in Physics. Second, the Big Bang explains the abundance of light elements in the universe. These elements, primarily hydrogen and helium, were formed during the first few minutes of the universe. These elements, like hydrogen and helium, were created in the intense heat of the early universe. The conditions were just right for nuclear fusion to occur, creating these light elements. Their proportions today match the predictions of the Big Bang model. This consistency between observation and theory is a strong indicator that the Big Bang model is accurate. Third, we see the large-scale structure of the universe. Galaxies are not randomly scattered but form a complex web of clusters and superclusters. Galaxies are not randomly scattered. They form clusters and superclusters, creating a kind of cosmic web. This structure is a direct result of the initial conditions set by the Big Bang. They form clusters and superclusters, creating a kind of cosmic web. This intricate pattern of galaxies and voids is a fingerprint of the universe's early moments. This structure also points back to the conditions created by the Big Bang. The distribution of galaxies and the cosmic web align with simulations based on the Big Bang model. Finally, we observe the redshift of galaxies. This phenomenon occurs because the universe is expanding, causing the light from distant galaxies to stretch and shift towards the red end of the spectrum. As light travels through the expanding universe, its wavelength gets stretched. This redshift is a clear indicator of the universe's expansion, a cornerstone of the Big Bang theory. This makes the light appear redder. The farther away a galaxy, the more redshifted its light, indicating it's moving away from us. This observation is consistent with an expanding universe. The farther away a galaxy, the more redshifted its light, indicating it's moving away from us. This observation provides strong evidence for an expanding universe. Together, these pieces of evidence paint a compelling picture of a universe that began with a Big Bang and has been evolving ever since. It's easy to imagine the Big Bang as a massive explosion, but that's not quite right. Explosions happen at a specific point in space and send matter outward. The Big Bang was different. Instead of an explosion, think of the Big Bang as an expansion. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move further apart. The dots themselves aren't moving, the space between them is increasing. Similarly, in the Big Bang, space itself expanded. Galaxies are like the dots on the balloon, moving apart as the universe expands. This expansion is still happening today, pushing galaxies further apart. The Big Bang was not an event in space, it was the beginning of space itself. It didn't happen at a single point, rather it happened everywhere at once. The Big Bang theory describes the universe expanding from a hot, dense state. But what about the very beginning, the moment of the Big Bang itself? Here, things get a little more complicated. The Big Bang theory doesn't tell us what happened at time zero. Our current understanding of physics breaks down at this point. We simply don't have the tools to describe the conditions of infinite density and temperature. Einstein's theory of general relativity predicts a singularity at the Big Bang. A singularity is a point of infinite density and curvature in spacetime. But singularities are often a sign that our theories are incomplete. So, was the Big Bang the true beginning of everything, including time? It's possible, but we don't know for sure. The very concept of time might be different in the extreme conditions of the early universe. Section 5. Before the beginning, inflationary cosmology. While the Big Bang theory is our best explanation for the early universe, it leaves some questions unanswered. For example, why is the universe so uniform on a large scale? Why does it have a specific temperature? Inflationary cosmology attempts to answer these questions. It suggests that a fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. This rapid expansion, driven by a hypothetical field called the inflaton field, stretched the universe to an enormous size, smoothing out any initial irregularities. Inflationary cosmology solves some of the Big Bang's puzzles and provides a mechanism for the formation of large-scale structures in the universe. It's an elegant extension of the Big Bang theory that helps us understand the universe's earliest moments. Section 6. Quantum gravity, a new understanding. To truly understand the Big Bang, we need a theory that combines the two pillars of modern physics, general relativity and quantum mechanics. These two theories have been the cornerstone of our understanding of the universe, yet they describe very different realms. General relativity describes the universe on a large scale: stars, galaxies, and gravity. It explains how massive objects warp the fabric of space-time, creating the force we perceive as gravity. Quantum mechanics describes the universe on a very small scale: atoms and subatomic particles. It delves into the strange and often counterintuitive behaviors of particles at the quantum level. However, these two theories don't always play well together. They often provide conflicting descriptions of reality, especially under extreme conditions. They break down when trying to describe the extreme conditions of the Big Bang singularity. At this point, the densities and energies are so high that our current understanding fails. This is where quantum gravity comes in. It aims to bridge the gap between general relativity and quantum mechanics, providing a unified description of all fundamental forces. Quantum gravity is a theoretical framework that seeks to unify general relativity and quantum mechanics. It attempts to describe the gravitational force in terms of quantum fields. It's still a work in progress, but it holds the key to understanding the universe's very beginning. Researchers are exploring various approaches, such as string theory and loop quantum gravity. With quantum gravity, we might be able to peer beyond the Big Bang singularity. This could open up new realms of knowledge and understanding. It could reveal a new understanding of space, time, and the origin of the universe. The quest for quantum gravity is not just about solving a scientific puzzle, it's about uncovering the fundamental nature of reality itself. Section 7. Multiverse and eternal inflation. The concept of the multiverse is a mind-bending idea that suggests our universe is just one of many. While it might sound like science fiction, the multiverse arises from some interpretations of inflationary cosmology and string theory. Eternal inflation, for example, suggests that inflation never completely stopped. Instead, it continues in different regions of space-time, creating bubble universes with their own laws of physics. Our universe might be just one of these bubbles in a vast multiverse. While the multiverse is highly speculative, it captures the imagination and pushes the boundaries of our understanding of the cosmos. Section 8. Cyclic and oscillatory models. Not all alternative theories propose a beginning to the universe. Cyclic and oscillatory models suggest that the Big Bang was not a unique event but part of an endless cycle of expansion and contraction. In these models, the universe expands for a period, then contracts in a big crunch, only to be reborn in another Big Bang. This cycle could repeat infinitely, with no beginning or end. While these models face their own challenges, they offer an intriguing alternative to the idea of a single beginning. Section 9. Conclusion: the Great Unknown. The Big Bang Theory has revolutionized our understanding of the universe. It provides a compelling explanation for its origin and evolution. However, the true beginning remains one of the greatest mysteries in science. While we have made incredible strides in cosmology, many questions remain unanswered. What happened at the Big Bang singularity? Was there a before? Is our universe just one of many? These questions drive us to continue exploring, searching for deeper truths about the cosmos. The journey to understand the universe's beginning is a testament to human curiosity and our relentless pursuit of knowledge. It is a journey that continues to inspire awe and wonder.